Hello, everyone. Welcome back to the Microcontroller Application Technology course. In this lesson, we will continue to study matrix keyboard circuits. In the previous lesson, we learned about the structure of matrix keyboard circuits. We understood how to use the row scanning method to identify the closed keys in matrix keyboard circuits. Today, we will learn a faster method than the row scanning method through a specific task: the line reversal method. This method will help us identify the closed keys in matrix keyboard circuits. First, let's look at the task requirements. Using 16 keys from K0 to Kf, arranged in a 4x4 matrix, to control the display of a single-digit display. When a key is pressed, the corresponding keyboard code of that key should be displayed on the display. We define the keyboard codes as follows. K0's code is 0, K1's code is 1. Kc's code is C. Kf's code is F. First, we will learn about the recognition of closed keys in a matrix keypad and the line reversal method. Compared to the row scanning method we learned in the previous class, the line reversal method scans faster. However, it requires that both the row and column lines in the hardware circuit can be used as both outputs and inputs, with pull-up resistors connected to +5 volts on both row and column lines. The microcontroller's P1 to P3 ports have internal pull-up resistors. It only takes 2 steps to determine the row and column values of the key being pressed. In the first step, set the row lines of the matrix keypad as output lines and the column lines as input lines. Set all row lines to output low level. When a column line shows a low level, it indicates the column where the key is located. For example, when K9 is pressed, the second row is shorted with the first column, lowering the voltage on the column line. Reading P1.1 port shows a low level, indicating that the pressed key is in the first column. If K2 is pressed, then the 0th row is shorted with the second column, lowering the voltage on the column line. Reading P1.2 port shows a low level, indicating that the pressed key is in the second column. In the second step, reverse the functionality of the row and column lines of the matrix keypad, making the row lines inputs and the column lines outputs. Set all column lines to output low level. When a row line shows a low level, it indicates the row where the key is located. Continuing with the example of K9 being pressed, the first column is shorted with the second row, lowering the voltage on the row line. Reading P1.6 port shows a low level, indicating that the pressed key is in the second row. If K2 is pressed, then the second column is shorted with the 0th row, lowering the voltage on the row line. Reading P1.4 port shows a low level, indicating that the pressed key is in the 0th row. This way, we can determine that the closed key K2 is in the second column and 0th row, and K9 is in the first column and second row. By storing their values, we get the keyboard codes corresponding to the matrix keypad. Using a switch statement, we can execute the necessary character to display on the numeric display once the corresponding keyboard code is identified, completing the task. It is important to note that key debouncing and waiting for key release are still necessary. Let's take a look at the specific program header file. Define the variable temp to store key values, declare a delay function. In the main function, first check if a key is pressed in debounce with delay. Then set P1 port rows as outputs and columns as inputs. Read column values. Reverse input and output. Read row values, and merge row and column values. Using a switch statement, determine the corresponding key value and output the corresponding segment display code. Finally, wait for the key to be released. After ensuring the program runs without errors, generate a hex file. loaded into the designed hardware circuit in Proteus simulation software. Press the keys, perform simulation debugging, and verify the test results. In the 18th row of this task, bitwise OR operation is used. This operation combines two characters or integers bit by bit through logical OR, resulting in 1 if either bit is 1, 0 if both bits are 0. Assuming the K2 key is pressed. First, read the value of P1 as the column value and store it in the variable temp. The current value of temp will be 0x0b, binary number 00001011. Second, read the value of P1 as 0xe0, binary number 11100000, as the column value, perform a bitwise OR operation with vertical bar, and finally get the value 0xeb, binary number 11101011, stored in temp, effectively merging the row and column values. When using the line reversal method to identify closed keys, if multiple keys are closed simultaneously, in the resulting row or column values, there will be more than one 0. As there is no corresponding value in the key recognition program for such situations, these cases can be considered as ghost keys and discarded. This method conveniently solves the issue of ghost keys. Through the study of controlling a single-digit display with a matrix keyboard, you should now understand how to use the line reversal method to identify closed keys in a matrix keyboard circuit and the usage of bitwise OR operations. Finally, please reflect on today's class and complete the following exercises to reinforce the knowledge learned today, further deepening your understanding. That concludes this lesson. See you in the next class.